Hello, my name is Martin, and today I'm presenting on behalf of my team, Microalu. This project implements a vision-based traffic light navigation system for a Puzzlebot mobile robot. The objective was to integrate computer vision, decision-making, and closed-loop waypoint control, so the robot could follow a path by reacting to a traffic light. The system was implemented using ROS2 with a shared ROS domain ID between the laptop, Rubik Pi, and the Jetson Nano with the Puzzlebot. The Rubik Pi runs the perception stack inside the Docker. The USB cam node publishes camera frames on image raw, and the traffic light detector node processes those frames using OpenCV. The detector publishes the stable traffic light state on the topic traffic light state. On the laptop, the path generator node publishes the next waypoint on the topic called goal. The autonomy node uses velocity encoder and velocity right and left to estimate the robot pose and publish the topic pose. Finally, the controller node receives pose, goal, and traffic light state, then publishes the velocity commands to on CMD to move the Puzzlebot. Here is our OpenCV vision pipeline. This pipeline starts with the image from image raw. Each frame is converted from BGR to HSV, then separates HSV. Masks are applied for red, yellow, and green. A brightness filter is also used to focus on the light that is actually active instead of detecting only the plastic color of the traffic light lens. After that, erosion and dilatation are applied to clean the mask. The algorithm detects candidate blobs and scores them using area multiplied by brightness. The final output is a stable red, yellow, green, or unknown. Dynamic ROI improves the efficiency and stability of the vision system. ROI means region of interest. Instead of processing the entire image, all the time the detector focuses on the region where the traffic light was recently found. This reduces unnecessary processing and helps the algorithm stay focused on the relevant object. However, if the robot moves or the traffic light changes position in the camera frame, the ROI could lose the target. So by this, the system performs a preventive, full-time search. This allows the detector to track locally while still being able to repair the traffic light if it moves. A limitation is that extreme side view angles can still reduce the visibility of the active lamp. The anti-flicker strategy was added to avoid unstable decisions caused by nose frames. A single frame can be misclassified because of reflection, motion blur, or camera noise. For that reason, the detector uses a temporal buffer. The buffer checks multiple recent detection before publishing a final state. This prevents the robot from reacting to isolated false detection. So the system also uses a yellow hold strategy. Since the yellow light can blink quickly, the detector keeps yellow active for a short time after detecting it. This makes the controller behavior smoother and prevents rapid switching between yellow and unknown. The traffic light state is sent to the controller through traffic light state topic. The controller first verifies that both pose and goal data are available. If the red lash is active, the controller produces zero velocity and keeps the current waypoint. This is important because the robot should not restart the trajectory after a red light. If the robot is turning and the angular PID aligns with the waypoint, if the robot is moving forward, the linear PID controls the distance error, while an angular correction reduces heading error. When yellow is detected, the velocity is scaled down. When the waypoint is reached, the controller publishes reached and waits for the next goal. Several improvements were implemented to make the system more robust. The anti-flicker buffer rejects isolated motion detection. Yellow holds improvement behavior when yellow light blinks quickly. The dynamic ROI tracking focuses image processing and on the defect traffic light region, while the red full frame search prevents the system from getting stuck in the target pose. Brightness-based scoring prioritizes the lamp that is actually on. And finally, red lash and speed scaling improves safetiness by stopping the robot on the red and reducing speed on yellow. And the system was tested using several traffic light scenarios. With green, the robot to continue the waypoint trajectory. With yellow, the robot reduces its speed while continuing the path. With red, the robot stops and remains stopped. When green appears again, the robot will resume the same waypoint instead of restarting the path. The main metrics used to evaluate the system were waypoint distance error, heading error, velocity command behavior, and traffic light reaction time. The final system integrated perception, decision logic, and closed loop control. OpenCV enabled reliable control segmentation and active light scoring. The controller adjusted velocity according to the traffic light state without resetting the waypoint navigation. Robustness improved through anti-flicker filtering, dynamic ROI tracking, and red latch safety logic. However, some limitations remain. Light reflections can reduce detection accuracy, and side view angles can hide the active lamp. Overall, the system achieves safe vision, closed loop navigation with traffic light-based speed control and stop behavior. In conclusion, implementation demonstrates how a mobile robot can combine computer vision and feedback control to react to its environment. The perception system provides a stable traffic light state, and the controller converts that state into the robot behavior while preserving waypoint navigation. Thank you.